your carrier is needed, I can help you. So let's talk about the production system and the asphaltene precipitation problem. Well, based on the audience, I have devised this presentation in two parts. The first part, I'll talk about the production system fundamental concepts. I'll talk about basic production system, how it works, and just basic. I will try to say it like a story. And later on, I will move to the advanced topic of asphaltene precipitation. And we'll talk about what is it, what's going on with that, and what are we doing currently. Let's look at our first slide here. And as I said, I will start from the very basic fundamental systems, fundamental production system. What is production system? What is it? And what are we doing as a production engineers? So today we will, act like we are all production engineers. We will forget the reservoir drilling, well test, or any other subject for now. We'll just talk as a production engineers and see what are we doing as a production engineers. Let's look at the production system. What is the production system, and what parts are included in the production system? Let's start with the reservoir. Here we have the reservoir. Okay, it's an oil reservoir here. It has some pressure. Then we install some plumbing system. Then we have here our Christmas tree, wellhead and Christmas tree. Then we have some pipelines. Then we have our separators. In the separator, the gas is going to other flaring or maybe for processing. Oil is going to the storage, and from the storage, it goes back to the refinery or whatever they want to do with it, so on. So basically, we as a production engineers, we are dealing with, I want to start the clipboard actually. Okay, I don't have it here. So we as a production engineers, what we are going to deal with, we are dealing with this production system, these plumbing artificial system that we are going to manage as a production engineers. And till these separators and till the storages, this is our responsibility to take the oil from this reservoir to store it inside these storage tanks. This is our responsibility and the production. So we have a lot of tasks to do in this all process, whatever is going on in the production field. Let me tell you, as a petroleum engineer, the production job is the most safest job and risk-free job you can do, especially at the field. Because when you are at the field, what you will be doing, you will be taking the data from here, monitoring all the system, and reporting to the head office. So this is the most safest job in oil industry you can have. Because when you are, for example, if you are a drilling engineer, you are responsible for drilling, and if blowout happens or something happens, it's a quite risky job. But when you are a reservoir engineer, you must be very careful in your calculation, economic calculations, because if your material balance goes wrong or if some data goes wrong, then again it's very risky there. So this is the most safest job as a production engineer. You just record data, send it to the office, and enjoy your time. Now let's look at what is the role of production engineers, what they do. As I said, the first job, what they do as a production engineer, they monitor the production. So every 12 hours, for example, you are hired as a production engineers, and some companies, they call them off-plot engineers. So you are hired as a production engineer, you are at the field, and for 12 hours, for 14 days or 28 days, what you will be doing, you will be monitoring the data, all whatever wells you are responsible for, let's say 5 wells you are responsible for, you will monitor the data, look at the data, sit on the screen, and after you record, you send that data to head office for the evaluation purpose. This is the job at the field side. Then we have another one, which is called the asset management planning. Now this work has been done in the offices. Now, what is the asset management plan? For example, how many wells you are going to have in this field. For example, okay, right now we have 5 wells. What is the next target? Should we drill 2 more wells? What is the production estimation you are doing? So you have to really work with the reservoir engineering team to plan out your assets, how much more well you want to put. And for example, now, okay, you have a production system here and you put the storage here. Now your storage has capacity, let's say only 100 barrels per day. Here. And here at the Christmas tree, you are producing 200, you have capacity of 200 barrels per day. So your storage is 100 barrels per day, you are producing 200 barrels. So what you should do? So what you are going to do, you will reduce from 200 to 100 because you don't have the storage. So part of your job is to properly manage your assets at the top and design them properly. For example, if your well has capacity to produce 200 barrels per day, you should have storage. You should put another storage here, put 100 more, and then make it 200 here. That makes sense now. This is the asset management. You look at the number of wells, you look at your production facility, and you look at the surface facilities, what you have and what you have. And also, not only the storage, the separator that you design, it also needs a capacity of 200 barrels per day or so on. Let's look at the third work, what you are doing with the workover design. Workover design, sometimes what happens, we have a well and let's change this one now. Yeah. Now we have the well here again, and in this well, sometimes what happens, there are leakages happen here, or maybe the system breaks here, so on. So if something breaks, you have to fix it, or maybe there's a sand production, or maybe there's another formation damage. So there are a number of possible things that can happen inside this tubing, inside here, inside this place. There are a number of things that can happen. So if we want to fix them, we call it a workover job. So as a production engineer, you have to look at the workover job, but you will be specialized for it. Right? For example, as a production engineer, you will not be working on all of it. Either you will be working on production manager, okay, or you will be working in asset management, planning what is going on, or in the workover is a very big field. For example, you might be working as a sand control engineer, or you might be working as a fishing engineer, or you might be working as a completion engineer, or you might be working as a, let's say, the flow assurance engineer. So there are so many jobs that as a workover design and engineer you can do. Of course, you have to look at the size of the tubing, what size of Christmas tree, what size of separator, so what size of storage. So all of this you have to do it. And above all of them, it all come with the money. There's nothing for free. There's no free food. So you have to estimate the cost and budgeting for whatever you are doing at the surface. So as a production engineer, you need to estimate all the cost and so on. That's why when you look at the job, they require a lot of experience. Why they require a lot of experience? Because it's a very expensive jobs. And if you have experience, you can easily design all of this for your company and so on. On the other side, when you work as a production engineer, you definitely have to work with the reservoir engineer. You have to work with the government agencies and service companies like Schlumberger, Baker, and so on, and those things. Okay, so that is the general overview, like what is the production engineer, what they do. So they have, as I said now, they have a lot of responsibilities to do and so on in this case. Now let's look at the company. What company expects from you? Okay, now let's say you are a production engineer. And as a production engineer, company hired you. They are paying you a very good salary, let's say $5,000 a month. It's a huge salary. So if they are paying you $5,000 a month, what they are expecting from you? They expect something good from you. If they invest 5,000, they want return more than 5,000. So what they want? They want to increase their production rates. So the mentality of the production engineer, when you are a production engineer, so you should be like, think how I can increase the production rates. You can increase, definitely, you can do, maybe do the workover on the well. Maybe the well has any problem, you are going to solve that problem, design the solution for that problem. You can increase the number of wells. So you are sitting in office. Okay, the brain is in office, not in the field. Field worker are executors. They just execute the job. They just look how they can execute the jobs and so on. But the one who are sitting in the main office, they are the one who have the brain, who have the softwares, who are thinking, analyzing, researching what they should do, how they should do, and so on. So what oil company wants from you? Maximum production rate. Let's say today's price is $50 per barrel, today's price. And if you are producing, let's say 100 barrels per day, so you are making 5,000 barrels per day, $5,000 a day. But if you work as a production engineer, if you just increase, let's say some of the production, let's say you increase the 10 barrels of production, it becomes 110. So you increase $500 per day, you increase their money. So per month, how much it will be? So it's 15,000. So if you have 5 wells like this, so the point is that there's you as a production engineer, they always say how we can increase the production, and you must have some idea how we can increase the production. So there are ways you can increase the production by, as I said, work on your well, see what is going on with your well, and drill more wells, you can say, and so on. The other thing is the economic longevity. Means you have to do your job safely. So you don't want to ruin your wells. You don't want to do something with your well shut off, or create more problems, and there's production from 100 goes to 0. It becomes 0. So they don't want this. So you have to be very careful what you are planning, because they want you to increase the production, not decrease the production. So you have to, what they are looking for, they want to increase the economic life of the well. And definitely they don't want to shut in the well for a long time, whatever job you are designing and so on. So the company, what he expects from you, increase production rates, increase the life of the wells, and just keep your wells on all the time. That's what they are looking for all the time. Here is the oil company. I mean, how they start making the money. This phase, the first phase, is the exploration phase. They don't really make a lot of money. And in the project building phase, they drill number of wells. Let's say they drill 3 or 4 wells. And then this is the main period where they make the money. And in the last one, they do some artificial lift, they put some pump, they try to increase the production and so on. So mainly there are these 2 parts are the main parts that where they make the money. And these 2 parts is the where they invest the money, exploration and development, because they are drilling so many new wells, they are drilling, completing new wells. So oil companies is basically here investing more, and here they will take out their return. In the end, we are all dealing with oil industry. Oil industry means we are dealing with money, and we are working to increase the profits for the company. That's our main job here. So here you see the operating phase. Here, the income basically starts from in the second and third phase. Okay. These 2 phases, there's no income, but we are just investing from our pockets or from the loans or for whatever we are doing. But this is the initial operating cost that we are dealing with here in the same time. Okay, this is the first expectation from the company: maximize production rate, maximize the long time of the well, life of the well, minimum downtime, do not shut the wells, keep them open, and that's what they are planning for it. On the other side, when we look at the cost, they want to minimize the cost. Okay, for example, you are designing a storage. Okay, the well has capacity to produce 200 barrels per day. Okay, you put the storage 400 barrels per day. Okay, definitely this will be expensive. Or if you put 200 barrels per day, okay, or you can put 100 barrels per day. You must listen to your well, how much your well can produce. If your well can produce 200 barrels per day and you are installing 400 barrels per day storage tanks, it means that you are increasing the capital cost. Capital cost is the one which you invest at the beginning of the project, whatever equipment you are bringing or so on. For example, when you are buying your phone, that is your capital cost. When you are purchasing is monthly subscription for internet, or let's say the prepaid cards, this is the operating cost. So there's a difference between capital and operating. So capital cost is the one which you invest in the beginning to start the project. So here's in the capital cost, your storage tank, separators, completion, drilling, all is your capital cost there. So you must be very careful. You don't have to increase the cost of the project for nothing. Okay, because everything costs money there. So if your well has capacity to produce 200 barrels per day, you should be able to design this 200 barrels per day, neither 101. No, this is not desirable, because later on you will need one more. You will increase the cost later on. So you are not really a good engineer because you didn't design well. On the other side, if you look for the story 400 barrels per day, again, it will be too much. So you don't have to go that high and increase the cost. So this is the capital cost that you have to be careful. Minimize the production cost. When we talk about minimize the production cost, means try to keep it natural, the well natural. Do not put any artificial lift equipment early stage, or try to maintain the pressures and so on. So this will keep the production cost low. Number of people you hire, the salaries you give them, and so on. So you as a production manager, you have to look into the cost for everything and so on. If you want to do the hydraulic fracking, treatments, and so on, so you have to minimize those treatment costs. So they don't want to, simply the company don't want to invest anything. So you have to push it so they can invest. Okay, so whatever their effort will be, they don't want to invest, they want to make the best out of it. That's every business they do like this. So so as a production engineer, you will have minimum cost here, and you want to increase the production and make as much money as possible in this time. Now, as a production engineer, what are the main domains that we work on? We said that here that we monitor the production, we do our asset management, we have our workover designs, we have our equipment designs, and so on. Now let's look at the services that as a production engineer we can provide. You as a production engineer, you can work as an artificial lift engineer, or you can work on the asphalting problem, or you can work on the monitoring, diagnosis, and workover. Monitoring means you just monitor the data, send it to the office, sit in your office, and that's it. Or you can design the workover, for example, if there's a tubing problem, tubing leakage, or packer leakage, or any other leakages. So you can work on the workover things here and so on. Also, you can design the tubing size and other equipment that comes in this well performance category. So we'll talk about generally for all of them before we move on to that one. So this is just the general introduction of the production system. Now let's look at this video, which tells us how this
by dividing our producing well system into its major components.
Now let's look at the situation here. What is going on? We have an oil zone here. We have so far nothing. So what we will do in we will first start
the producing formation, tubing.
During the drilling process, we will install our casings like this one. This one casing, there's another casing. Then we install the perforation tubing. Then we perforate them. It means we create holes here. We have install our Christmas tree.
Choke, surface flow line, and separator.
We have our flow lines. Then we have our separator here.
Elements are sufficient to illustrate the concepts involved in describing the pressure flow rate relationships of our production system. All of the components are interrelated. We understand intuitively that fluids cannot be
So we as a production engineer, we manage this one and
produced on the surface at a higher rate than they flow out of the formation or are lifted up the tubing. We know that fluids flow from points of high pressure to low pressure. What we must do is show graphically how the pressure and flow rates for our system are related. We begin our discussion by dividing our producing well system into its major components: the producing formation, tubing, choke, surface flow line, and separator. These elements are sufficient to illustrate the concepts involved in describing the pressure flow rate relationships of our production system. All of the components are interrelated. We understand intuitively that fluids cannot be produced on the surface at a higher rate than they flow out of the formation or are lifted up the tubing. We know that fluids flow from points of high pressure to low pressure. What we must do is show graphically how the pressure and flow rates for our system are related.
Okay. So now, as we discussed here in this video, the first step is do the casing job. Okay. As I said, today's one we'll just talk about the fundamentals, how the production system is developed here. The first thing we run the casing. And what is the casing? Casing is just a pipe. It's just a pipe like at your home, which you use for plumbing system in your water tanks, and to the restrooms and everywhere. Those pipes, the same pipes, bigger size, better quality. So same size of pipes that we have, we put them inside the well during the drilling process. These casings here. And what is the objective? We don't want the formation to collapse while we drill, and we don't want to drill again and again. So we just want to go put the pipe, save it, and our well so that we can produce it. And other main job is that, as you know, during the drilling process, we are using the drilling fluids. And drilling fluids, if they go and mix with the fresh water, can create problem for us. So we keep casing the well so that the water drilling fluids we are using, we are producing the oil. It should not mix with the nearby fresh water formation, because the fresh water is very important for us and for our lifestyles and so on. And of course, we want to control the production and produce much of the oil from there. So now when we look at the casings, we have 5 different types of casing. We have mainly the conductor string, we have a surface pipe, we have the intermediate string, we have the production string, then we have some liners and tubing installed later on. Let's look at the typical size. Now the monitor that you are using right now, some of you might have 14-inch, some of you might, the screen you have right now in the computer that you are using, some of you might have 14-inch, some of you might have 15, 16-inch, some of you might have 22-inch, or some of you might have 32-inch of screen that you're using right now in your homes, or in your offices, or in your labs, or your laptops. So imagine the same thing we have. This is the 30-inch. 30-inch, you can imagine how big it is. Probably the length of your laptop. 2 laptop screens. So that's the size, that's the maximum size of the casing. But we don't produce from that much big the diameter of well. We produce just probably 2.5-inch from it. That's what I will talk about. So our first string that we talk about here, this one, is the 30-inch. And 30-inch, as I said, length of 2 laptop screens that you have right now, probably 15-inch by 15-inch. The second one is the 20-inch, and then we have the 30-inch. Then we have the 9-inch, and then is 7-inch. There is one thing which is important right now to know for all of you, that we don't do the drilling with the same size from top to the reservoir zone or the production zone in the same one. We don't do that. We do it in smaller steps. We have a larger diameter, then we reduce it, then we further reduce it, then we further reduce it, and then in the end we do the liner. We are not extending this liner, the one you see here, 7-inch liner, to the surface, because it's just increasing cost. Because if this can do the job, why should we extend it to the surface? So that's why, just to save the cost, we just run the liner and so on. Now, the 7-inch means the pipe that we are using is half of your the laptop screen that you are using right now. If you are using a 15-inch screen, and half of it means starting from this point till this point. So that's the maximum size, but still we don't produce from that big. Still, this one is big for our production. We just produce probably from 2.5-inch to 3-inch, 3.5-inch, maximum of that size of strings that we produce it. Let's look at the production casings and how they do the casings and so on. It's a very nice video which can share with you. So see this, we have the first casing, then we have the surface casing, then we have the intermediate casing, and then we have the production casing. That's how we do the casing job. And who designed this one? Is the production engineer. This is their job, to design the production screen. Let's look at it. As I said, we don't drill same well, same hole from the top to the bottom. We don't do that. We do it in step by step, from larger to the smaller. That's the process that we follow on. Here you can see what we do. We first do the cave-in. See, this is the cave-in. Cave-in means that there are rocks, they fall down inside. So when you drill and rock is falling down, then what is the point of it? So we have to save this. We don't want this caving in issue. So what we do, we put the conductor. Now, once we put this kind of a pipe, it means that the formation nearby cannot fall inside the hole and fill the hole, and we do it again. So that's why we put this conductor pipe here. Then we have the surface casing that we install it. As I said, these are the pipes, same pipes that you have at your home for plumbing system. Here we have the surface casing, then we have intermediate casing. Every pipe that we are putting should have a reason. Okay. For example, the surface casing you are putting, you want to save this fresh water. That's why you're putting this one. So you don't want, if you are injecting the drilling fluid, you don't want this drilling fluid to go from this point to this point here. Or if you are producing from this zone, so you don't want your oil to go there in the fresh water. So in either case, you don't want this. And also you don't want all these formations to fill in and fill up this one and block the oil to flow. Then what is the point to do all this drilling process? So we don't want that. So in order to avoid all of them, we do these casing jobs. And where is the here it is. So as I said, we don't go for straight, and we have a conductor pipe, then we have the surface, then we have the intermediate, and so on. And then we have the production casing here. Here's the conductor pipe, the first one that we do. And as I said, maximum 30 to 30 inch. And then we are putting the pipe. We first drill the hole, then we are putting the pipe here, and then we cement it so that it gets fixed there. It's the first thing that we do. And after that, we'll use this smaller size of a bit that will go inside this pipe and drill further.
Doctor, we have a question in chat box.
Do you have a question?
Someone asked, production engineer makes a casing design. What about the drilling engineer job?
Yeah, drilling engineers, they have a lot of service companies, they work there. For example, the casing may be designed by another service company. Usually the baker is hired or Weatherford is hired to do the casing job. Then there are other services companies that come. For example, drilling fluids, probably by Halliburton company. Maybe then you are designing the tubing size. So then tubing may be from the another company, or maybe you are doing the managed pressure drilling job. It could be by another story. Then you are doing the well test analysis on the drilling. So drilling engineering, once we are at the rig side, basically, once we have the rig here, this is the production system. So once we have basically so once we have, let's say, the rig here, and we are doing the drilling process here like this. So at this place, this one is designed by production engineers or completion engineers, usually the baker or but as I said, there's no only one company working on this well site location. There are multiple jobs going on. For example, we need to take the logs also. We need to look at what kind of formation we are dealing with here. So there should be a logging company, mud logging company. It's a separate company. They will do the mud logging. Then there will be another company who will be doing the perforation company. Then there will be another company who will be doing the testing, well testing. They will look at the pressures and temperatures of the downhole and take the samples and so on. Then there will be a company maybe doing the managed pressure drilling. So there are a number of companies, number of engineers, service company engineers, they will be working there on the drilling site and so on at the same time. But now, if you are working as a production engineer, as I said, you might be paid $1,000. Okay, But your friend graduated from the same university, from the same department, and he might be working for Schlumberger. He came as a, let's say, the completion engineers, and he's doing the casing job or so on. So he will be paid more than you. For example, usually the service companies, they pay more than the operating company. Operating company is the one who is the operator of the company, and they hired you just to go represent the company there as a production engineer. On the other side, or as a drilling engineer by the company. On the other side, the service company, they are paid higher because they are here doing the job. But who is the boss? The one who is the operator, the engineer from the operator company, because they can kick out anyone from the field. They can bring in anyone in the field. So they are the bosses, but they are less paid than the service company engineers. And as I said, there's a clash going on at the drilling site always. The company who is paying for the drilling wants to reduce the cost. That's why you are here. You look at what's going on. And those who owns the rig, those who are doing the rig thing, they want to increase the cost. So the drilling engineer by the Schlumberger, he wants to increase the cost because that's how they make money. And you, from the company side, from the operator side, you want to reduce the cost because you save the money from them. So that's what is going on. So you have to be technically very sharp, mentally very strong to be there, so that you can save the cost or you can increase the cost in either way. So it's very tricky situation when you are at the rig site. So yes, there are production engineers who will be specialized in the casing designs, and they run the casings there at the rig site. Usually bakers, they have a good completion design or casing design programs. So you see now from the bigger one, then we go to the smaller. Here you can see larger and smaller. Okay. The question is, what about the drilling engineer's job? Drilling engineer's job is to do the drilling process. They design the drilling engineering. I mean, look what kind of bit you are using, what kind of drilling rate, RPM you are using, what kind of drilling fluid you are injecting, what kind of penetration rate you are using, what kind of drill string design, what kind of drill color, how many drill colors you are using, what kind of drill size you are using, how much the weight on bit you are putting, what is the target depth. So you as a drilling engineer, you are dealing with the drilling engineering, not as a production engineer. Production engineer and drilling engineers are different. Drilling engineer deal with drilling the well, and production engineers usually they are doing with the casing, completion, tubing, design, and later on producing it. Okay. In some areas we have district engineers in fields. Is it equivalent to office job, which have been mentioned as the brain? The brain, those who are working in the offices, they are using the software simulations and designing. So they are using their brain and research and so on. Once they have designed, sometimes they go to the district along with the district officer, they facilitate it. So those who are working in the field job as a district, they just facilitate for the people who are coming from other companies. For example, there's a workover job you're doing. Weatherford has to do it. So Weatherford will contact that district engineer, and the company will ask them. So they are doing, let's say, the fracking job. So kindly assist with them. So you are the representative of production company. You will communicate with your company, tell them what they are doing, how they are doing. So you will look at their values and parameters, take the data, send it to office. So you will be working as a liaison, as a communication officer between the Weatherford company at the field to the office where your other bosses, other friends are sitting, doing the designing and so on. So you'll be working as the medium to communication between both of them, as well as, of course, you are also an engineer. You're also looking what they are doing, how they are doing. If they are doing something wrong, you have to stop it. So at the same time, you're doing it. That's why you must have some experience there when you work as a production engineers. So here is the another casing they're cementing they're doing. Here you can see they reduce now this bit design. They are changing the bit size. They are changing the bit. Of course, this is all a drilling engineering work that they are planning. So now they have put all the casings and so on. This is the production casing. And then they install the tubing inside. We'll talk about it and so on. Here's the perforation job. They make the holes because once you do the casing and cementing, there is no way you can communicate with the reservoir. All you have to do, you have to perforate and create the hole so that oil can flow from here to the surface. Here you can see. So now oil can flow and go towards the surface and so on. This is the liner. It has already a perforation. So that was before they did the perforation. Now we have another technique. We install just a liner with already pre-slotted liners. So it has already some holes and so on. Yeah. By the way, those who are at office, what kind of software they are using? They are using the PipeSim. They are using the Olga. They are using the some other Petroleum expert software. You can say the GAP and so on. These kind of softwares they are using in the office to design their production facilities and so on. Okay. Now the question is, okay, we have these kind of casings, but not only we do the cementing here, not only we do the cementing here or we fix them, but we have something which can hang it from there. It's like a hanger of the clothing at your home, in your wardrobe. How you hang the clothes? You have hangers there. That way you can hang your clothes there. Same way here, we have installed some hangers here, and we call it as the wellhead. Wellhead is what? It's just assembly of hangers. So what it does, let me show you. Here it is. What it does, if you have a casing will be hanged here. Here we have the casing hanger. So casing will be hanged here. By here, then it will be sealed from this one. So that's this assembly of the wellheads that we have, and above it we put the Christmas tree and so on. So basically, in the wellhead we have three components. We have the casing bowl, we have the casing hanger, and we have the tubing head. Tubing head is same just for the tubing. Casing is for the casing. We have two things. First, we do the casing as I showed you here, and in the last we install this tubing. Here they have shown the bit, but let's assume it's not a bit. So we do have the tubing here in the end. So what we do here, after the casing, we install the tubing, and we have all of this assembly is controlled by the wellhead here at the top, and that's how we do the one. So how it will look like in the end, the overall diagram, if we sketch it, we will have the number one, then we will have another casing here. Okay, and what it will be done, then we will have here wellhead, this wellhead. Above the wellhead, we will install the Christmas tree. What is the job of this wellhead? It is basically hanging all those strings, this string or this string. It is just hanging the one. In open hole completions, we don't have open hole completions anymore. It's just a very ideal situation when you have nothing. You do the open hole. You have very solid formation. So we don't have really a lot of open hole completions anymore. Yes, we run the tubing. In open hole completion, it depends. Sometimes we do, sometimes we don't do. But usually, what I remember that now we don't have open hole completions in this one. This is the wellhead here. No, this is just to show the casing diagram. It's not completed. Okay, this is just to show the diagram. This is here we have to install the liner or something here. This is just right now we are dealing with the casing stuff. Yeah, so we didn't go to that level right now. We are just discussing the casing diagrams, and we are discussing the wellheads here at the same time. We are, I mean, as I said, we are just slowly going on casing, completion, and the other activities that we do on the production system. Our topic is production system. We understand how we start, how we do the casing, and how we move ahead with this casing. So we have the casing valve, all is the wellhead system. And on top of this, we have a tubing hanger. Tubing is a small pipe, and this probably is a 2.5 inch. And you can imagine your laptop screen probably is 14 inch. So 2.5 inch probably is this size to this size, maybe to this size. You know, it's that small from where we actually produce. So this one. So here we put it here, the wellhead. On this wellhead, we have the Christmas tree placed here. Here's the Christmas tree. This is placed on the wellhead at the same time. So below here, you just see that we have the Christmas tree here. And the last thing you see here is the tubing hanger. But if you remove this place, you see that we have the casing hangers there. And of course, we look into the casing hangers. When you are at the field, there are also pressure gauges in those wellheads. Why? Because if there are usually we cement all of this. We cement all these sections. We cement all these sections. So there are pressure gauges here, which tell us the pressures in each of them. So ideally, there should be no pressure because it is all cemented. It should be all empty. But if you see that there is some pressure here, it means there is some leakage here. That's why the pressure is generating. So we do follow all the pressure gauges to see how much pressure they have. If they have more pressure, it means there is some leakage in the cement or something. So we keep following all of this and so on. Here we have that. So after you complete your well, you do your casings and then install the tubing. Then you have the system of production system, which looks like this one, which has Christmas tree at the top. Then we have the wellheads, and then we install the safety valve. The purpose of the safety valve, which has a line also here, we install a safety valve here because what if somebody, all this Christmas tree fails? Christmas tree can fail for multiple reasons. Maybe there's a war going on. So this has started after 9/11, this thing. If there's a war going on and if somehow the Christmas tree is destroyed. So if the Christmas tree is destroyed, there will be uncontrolled flow of formation coming out. So we need a valve which can keep it closed. If some war happens, something happens, the Christmas tree is blocked. So now they install the SSSV safety valve here, which is operated through some fluid through this line, as you can see here. So yeah, so here in this one. Then sometimes we early design the gas lift. Gas lift is an artificial lift method. Then we have some packers here. So that's the overall sketch of the production system. Okay. So now let's look at the production system, how actually it all looks in reality. Okay. Hey guys, the engineers. Here we are. This is what we call. This is what they call Christmas tree. See? It's simple. You see? Actuator, you see that actuator? This is actually a valve.
the rotary valve. This is gauges, pressure gauges on it. This is working now. Working flow line. See that valve, that pressure gauge over there?
Yes, it is gas well. And safety valves are on every well. There is nowadays safety valve, and we keep monitoring the safety valve, because as I said, if something happens to this one, so we keep monitoring. So now let's look at, as a production engineer, me as a production engineer, I will not look at this picture as it is. So for me, what it is inside it, this one. Yeah, we have here the Christmas tree. Here we have, below this Christmas tree, we have here the wellhead, and below this one, if you go and see, you will see a wellhead, which is, and below this wellhead, definitely we will have our casings, the conductor pipes. Okay, the conductor pipe will be like this. Then it will have another pipe casing. Then it will have another casing. Then finally there will be a tubing, which we have here below. Okay. This is the, I mean, as a production engineer, we know that the downhole, we will have assembly like this one. Then surface, we have facility like this one. And then we have our work with the flow line, which is transporting whatever fluid which is coming out, and so on. And definitely we have all the gauges here going on here at the same time. So this is the production system that we deal as a production engineers, and so on. Any questions here?
Okay.
Yeah, gaskets are installed just to avoid the leakages here. Okay, we don't want any leakages, and we have different sockets. So if we have two lines here, if one line fails, okay, if one line fails, this one, for example, so we have another alternate line. We have double things going on. One safety, one as a safety, and one as the other one which is operating one. So we always have two lines. One, and again, one is the actuated operator, one which is operated through the hydraulic fluids, and one by the manual hands. So usually these wells are operated through the DCS system from the well one. And then we have one more here, which is the swab one. Whenever you do the workover job, you are sending the coil tube something, so which goes down from here. So we have the swab wall. But usually, as you see, there are two lines just for the safety purpose. If one fails, we go for the other. That's gaskets definitely for the leakages. So we, of course, we don't want any leakage here. We have to be very careful and so on. So as I said, now when we look at the production system here, like this one, how we should look at the production system. We as a production engineers, we don't look at, okay, there's a Christmas tree, or maybe those flow lines here. We look at it as a game of pressure. Oil industry, production engineering is all the game of pressures. Let's look at the reservoir. In the reservoir, we have the pressures here. And from the pressures, the oil, let's say we have the oil here. Now this oil starts flowing from here from the perforation. So what happens as a production engineer, you must imagine that the oil cannot flow from this point to this point unless there is a pressure difference. There is a delta P. Let's say here is 2000. Here maybe is 1000 or 1500. So there's always a change in pressure from this point to this point. So pressure is reducing. That's why the oil is flowing from high pressure to the low temperature or low pressure. So likewise, we have some pressure loss. And why this pressure loss is happening here? The pressure losses here are happening because of the restrictions, the perforation restriction, because they are very restricted here. Okay. In this case. So if we have the oil which is flowing and is stuck here, is restricted here, so there is definitely a pressure. And once this oil comes inside the perforation, try to go inside the tubing, which is, as I said, is only probably 2.5 inch from here to here, this size. So it's very small size, and again, there's a pressure. And then you have the restriction. As I said, we have a safety valve, we have a gas lift valve, we might have installed any other equipment. So there could be further diameter restrictions here, which can reduce the production rates. So there are pressure losses starting from the reservoir till the separator. And of course, at the Christmas tree, here we have the pressure losses. Here we have the pressure loss. We as a production engineer, how we look at it, we don't want a lot of pressure losses. If our pressure is lost too much, oil will not reach to the surface. So we look at the production system. I'm talking about the production engineers who are working in offices, who are dealing with the production system and looking at the pressures. Every morning, the field production engineers, they send the production pressure history, production history, how much oil is produced, how much gas is produced, how much water is produced, what was the GOR, what is the pressure, what is the temperature, how much is the, so all this data every morning, every 12 hours, they are sending to the office. And office, then they are analyzing this one. So they keep looking at the pressures and the production history, what is coming from the field to the office, and they keep analyzing these pressures here and so on. So here, look at the pressure. So this pressure here, this is a diagram of the pressures, how the pressure is reducing from the top to the bottom, starting from the reservoir, inside the plumbing system, at the surface facility. So I'm talking about starting from here, step 1. Yeah, I mean, here is step 1, step 2, step 3, how the pressure is reducing. Let's imagine we have the pressure here 3000 psi and the reservoir. So till it reaches to the well bore, see how much pressure is lost. Maybe we lose here at least 800 to 900 psi. Then we have some restriction in the tubing. The pressure is reduced here. So if you are working as a production engineer in office, one of your job is to keep looking at this kind of a diagram, keep optimizing the pressure, and look at it, why the pressure has dropped. How much is the reservoir pressure and how much we are receiving at the wellhead or so on. So this is called the well performance. You look at the performance of your well. And what kind of performance you are looking into it? You are looking at the production rates. You are looking at the pressures. Flow rates, pressures, flow rates, pressure. You are looking into this one. So this is the final pressure at the separator. So imagine your reservoir has a pressure of 3000 psi, and here you are at the separator probably 100 psi. So a lot of pressure has been reduced. You as a well performance engineer, your job will be to keep optimizing these pressures so that at least you can receive oil at the surface. There are cases that pressure goes dead because of pressure losses or restrictions, or maybe the tubing size you put was bigger, or maybe tubing size you put was very smaller, and so on. And the another question you asked me, can an open hole, should we put the tubing or not?
Hang on. Engineers.
There was the question right now, for example, if we have the open hole casing, should we put for example, we have done like this. Now this is our reservoir. Okay, we drilled our well here. Okay, now this hole is not a casing. So for example, now the reservoir pressure is 2000 psi. The open hole that you have here, open hole, has the diameter of, let's say, 15 inch or let's say 10 inch. Now, if the oil which will try to go through this 10 inch open diameter, maybe the pressure here at the reservoir may not be enough so that your oil can go towards the surface. May not be enough. It's not necessary. The pressure may be enough from the bottom to the surface because the opening is just too big. It's 10 inch. On the other side, what you do, you don't install the 10 inch. You have an open hole here and you install some tubings. Sorry, my hand. So, and you case it. Now, what happened? The tubing reduces the diameter to 2.5 inch. Now it is a very narrow diameter pipe. So now you still have open hole casing, but what you do, you're trying to do the tubing so your oil can flow inside this restricted one. Now here oil will flow more faster because what you do, You have restricted the diameter of the hole, so the oil can flow easily from top to bottom. Okay. Well test engineers, usually they have a separate domain. Well testing engineers, they do have the well testing data, all of the testing data, production engineers, because when you do the workover jobs, you need the well test results. Now, for example, if there's a formation damage, you do the well test, because well tests tell you the skin factor. And the skin factor is a very valuable thing that you need for production engineering evaluation, or for production cost, the forecast, the skin factor. So the well test, pressure buildup test, pressure drawdown test, they tell you the those kind of techniques that they tell you what is the skin factor. And skin factor, what is it? It is evaluation of the damage, permeability damage inside the hole. For example, if there's some plugging because of drilling fluid or something and your oil cannot flow, we call it a skin. So if they have a high skin, we call it, let's say 10 skin number 10, it means that well is very highly damaged. So how we know that? We do the well test. We do the well test, pressure buildup test, and pressure buildup will tell us. So production engineers do evaluate the well test data, but they don't do, as I said, production engineer is a very fast field. You may work as a well test engineer, but then that will be the only specialized thing you will be doing. You will not be working in other parts of it. So if you are working as a testing engineer, you will work as a testing. If you are looking at the production forecast, okay, production engineer, production technology, they are the same terminologies. It depends on company to company. Some companies, they call them production technology engineer. Some they call them production engineers. Some even call them off-float engineers. Some call them the field production engineers. Some call them the production the engineer at the office. So it depends. Some they call them, they don't even term them production engineers. They call them directly completion engineer, well test engineer. So completion engineer, well test engineer, they call them their own specialized name, sand control engineer. So production engineer is a very broad term actually. So you will not be working as a very, like in a broad term, you will have a very specialized name tag. For example, you might be doing the asphaltene control. So that will be the flow assurance engineer. You might be a testing engineer. So you will be, two different departments for everything that we have. That's correct. Okay, what kind of departments here you have in Egypt? As I said, there are two. One is working in the field, other one is the office. In office, you might have different departments. Somebody working on production forecasting, somebody is working on workover, somebody working on. So there are so many people working together as a team in all those on the issues that we just talked about, all of them. So when we talk about the production pressure losses here, okay, so we as a production engineer, we want to reduce the pressure losses. That's our main job. How we can do that? Let's look at it. Okay. And we as a production engineer, we can do the system product pressure drop optimization. We call it a nodal analysis. So if you are in a field office, in the head office, you will be doing this one, system pressure drop optimization. So we call it here as a production engineer, there's another department, we call it nodal analysis. So you will be using some software, you will be doing IPR analysis, that's a separate subject you will be dealing with. So you will be handling the performance of this well. So you will do the nodal analysis, how much pressure is dropped there, how much pressure is dropped there, how you can improve it, how you can reduce it. So you will be doing the well performance evaluation here. Maybe in the end, you might have to change the tubing size and so on. The other thing which the reservoir engineers, they do, they inject the fluids. We call it a EOR, enhanced oil recovery. Maybe you are injecting the water, maybe you are injecting the gas. So for example, you might have one well here. So this is the production well, and this is the surface of the earth. So you might have another well here. Now purpose here maybe is to inject something, and that will go and push this oil, increase its pressure so that the oil can go ahead. So we can be doing the fluid injection. It's an advanced technology. Not too many people are doing, but there are a lot of simulation studies you can do. For your graduation projects, you can do such kind of projects: gas flooding, water flooding, this one, system pressure optimize. So these are all the graduation projects. So once you will be in final year, you can take one of project, and I can help you with these things and so on. Sometimes we don't inject it. The most easiest thing what we can do, we can install some jet pumps, artificial lift methods, some pumps here, which can lift the oil from bottom to the top. We will talk about it in the next few slides and so on. Yeah. Then we install the pumps to lift oil to the surface. We definitely look into the well design. We as a production engineer, our main job is to look at our production system, how we can improve it. Maybe we can reduce the size of this tubing, or maybe we can increase the size of this tubing. Maybe the separator we have the capacity to produce more. Maybe the separator has no capacity to manage that much production. Okay. Maybe there is a sand control problem. Maybe there is a problem of asphalting. So you as a production engineer managing all of these things here and so on. Here's the pressure drops things that we look into it. Okay. Now, as you said, before, can well test a production engineer work as a well test engineer? Well, we need sometime what happens during the drilling, when we are drilling and when we have the rig here, and then we have a tubing string. So the drilling fluid, sometimes what happens goes inside here, drilling fluids, and which causes the damage. Or maybe you are using the Becker fluids, or maybe you are using any workover fluid. So fluid can create a permeability damage here, which is, we call it a skin factor. So if there's a damage here, our porosity or permeability is blocked. We cannot do anything. What should we do? So we artificially stimulate. We do the fracturing, like you are smashing the window and cracking it, making holes out of it. So what we do, we send a hydraulic fluid down, which frack this area to create artificial permeability so that we can do it. So this is one of the job of the production engineer. What they do the hydraulic fracking or acidizing job in order to do the well stimulation. What is the purpose? Why we do that? We have to improve the permeability. We don't want to bypass the fluid and so on. So this is how we do the stimulation. So what are the stimulation techniques that we have? We do the hydraulic fracking, very popular in America here about the fracking, or then we have acid fracking going on at the same time. So let's look at how hydraulic fracking works. What I just explained.
And carry the rock fragment cutting. Hydraulic fracturing has provided safe extraction of oil and natural gas from underground shale formations for more than 60 years. The technology continues to improve, increasing access to abundant energy sources.
I will talk about this.
Hydraulic fracturing has provided safe extraction of oil and natural gas from underground shale formations for more than 60 years. The technology continues to improve, increasing access to abundant energy sources while limiting environmental impact. Take a look at the process today in underground shale formations. The initial wellbore is drilled using a drill pipe and bit. Drilling mud is pumped down through the drill pipe to cool and lubricate the drill bit. Mud also helps stabilize the wellbore and carry the rock fragment cuttings to the surface. The drilling continues well past the aquifer or groundwater level. Thousands of feet of rock separate shale reserves from the lowest groundwater reservoir. At this point, the drill pipe and bit are removed. and a steel tube called surface casing is set inside the well. The tube stabilizes the well sides, creating a protective barrier for both the well stream and any underground freshwater reservoirs. Cement is then pumped into the well through and out the casing, displacing any remaining drilling fluids and permanently securing the casing in place. By filling the gap between the casing and well bore, the cement creates a seal, protecting groundwater from contamination and keeping outside materials from entering the well flow. Once the first layer of casing is in place, it is pressure tested to ensure hydrocarbons and other fluids do not seep out into the formation as they are brought to the surface. The pipe and drill bit are lowered back into the well where the drilling continues. Another layer of casing and cementing is then constructed to create a second permanent protective barrier. Multiple layers of casing and cementing are critical to safe well construction and drinking water protection. About 500 feet above the hydrocarbon-bearing shale formation, a specific downhole drilling motor with sophisticated measuring instruments begins the angle drilling to create a horizontal path to penetrate the targeted layer of gas or oil-bearing shale. Once the desired horizontal distance is reached, the casing and cementing process continues through the entire length of the well bore. A perforating tool is then inserted into the well, creating holes in the shale layer, allowing hydrocarbons to enter the well stream.
So this is basically a fracking job where we create holes here.
When the perforating tool is removed, fracturing fluid, made of mostly water and sand, is pumped into the well, opening tiny fractures deep into the shale. Water is removed, but the sand remains, holding the fractures open and allowing gas to travel from the shale out into the well. From the shale completed, the plugs are
The
removed.
well
and gas
intervention
flows
is
to
the
surface.
workovers job. Those
The
who
entire
have any
drilling
other
process
problem,
takes about 2 to 3
so
months, but
they do the
hydraulic
workover job.
fracturing
This
takes
is the
only
fracking
days
engineer,
and can
fracking
allow for 20
engineers
to
directly.
40 years of energy production. Combining horizontal drilling and hydraulic fracturing reduces the footprint of drilling and makes it possible to produce oil and natural gas in places where previous technologies could not.
Usually we use the coil tubing when we do this. So coil tubing is a small, when you garden your trees at the home, you use the plastic rubber pipes. So we have a coil tubing unit, and the coil tubing unit basically, I mean, you're not sending the fracking fluid through this tubing string, the hard tubing. No, we have a specialized truck, we call it a coil tubing unit. The coil tubing unit has a coiled tubing, rubber tubing, which goes from this one to the bottom, and that is the one which is pumping the fluid and taking out the fluid at the same time. That's a specialized coil tubing unit that do this job. And well intervention engineer is the one who do the workover jobs. And the hydraulic fracking is the one the fracking engineers, they do this kind of job. Well intervention engineer is probably there's some change, you want to change the tubing size, so it's a well intervention thing which is going on. Okay, so that was about the hydraulic fracking, one of the job that production engineers they do. The other job is they install the artificial lift engineers. As I said, the production engineer, you don't have to do all jobs together. You will just say select one of it and be specialized with it. So that will be the production engineers. That's how they deal with it. So we have a number of artificial lift methods, especially the rod pump here, famous in the United States. They use a lot of rod pumps here. And then we have so what they do, sometimes, here's the picture. Sometimes the well does not have enough pressure, so you can take out the oil from the reservoir to the surface. It does not have enough pressure. Could be any reason, could be bad tubing selection, could be a lot of restrictions, so it doesn't come. So what we do in this case, we have different techniques we install at the surface, the artificial lift methods through which we can take out the one. Okay, so the most famous right now here in the States is this one. So let's look at it. How does it work? Yeah, the plumbing system. Plumbing system is the plumbing system. Plumbing system, basically, this is all your plumbing system. When I say plumbing system, is the assembly of pipes. So your casing, your tubing, the backers, the triple SV wall, this all is the plumbing. It's like at your home, you install artificially. So the natural thing is the reservoir itself, right? So the plumbing system, what does it mean? It means that all those assembly of pipes at Christmas tree is all the plumbing system, like at your home. So you want to open the tap water at your home, is the water is coming from your tank. So from the tank to the water in your toilets, this all is a plumbing system. It's an artificial assembly of pipes which takes the water from the tanks and reaches towards your restroom. Likewise, we have the oil in the reservoir. We have a Christmas tree at the surface. So all of this together, yeah, for the referencing, you can find out just plumbing system, oil plumbing system on Google. You can find out a lot of things about it. So we call it a plumbing system. So just search Google it like oil well plumbing system. It's just not the technical, it's just a non-technical word we use just to represent it. It's not a really since it is, we call it a plumbing system, so we just call it a plumbing system. It is a plumbing system, in fact. So let's look at the sucker rod pump, how they do the sucker rod pumping.
The stuffing box allows vertical movement of the rod string
there's
by
a rod,
providing a
it's
seal
traveling
around
up
the
and down.
polished rod, where it enters the tubing string. A lubricator is sometimes installed above the stuffing box to reduce wear on the stuffing box packing and polished rod.
So there's a rod. This rod goes
Individual
down.
sucker rods connected by rod couplings make up the rod string. Each rod in the string is coupled to the rod above it and supports the weight of all the rods below it. Each rod must be strong enough to support the weight of the rods below it, plus the weight of the well fluids in the tubing above the fluid level in the well. A rod pump is a relatively simple device and can be operated over long periods of time with minimum cost and maintenance. There are two classifications of sucker rod pumps: an insert or rod pump and tubing pump. The insert pump is installed on the rod string. A tubing pump is attached directly to the tubing. The simplest type of pump consists of two valves and moving plunger to control the flow and lifting of well fluids. With this type of pump, the plunger is connected to the bottom of the rod string. The pump is usually located at or above the producing zone. As the rod string is lifted by the surface pumping unit on the upstroke, it lifts the plunger inside the pump. Polished rods range in diameter from 1 to 1.5 inches and from 8 to 22 feet in length. As a rule of thumb, polished rods are usually 2 or 3 times the actual stroke length. This allows them to be reversed and reused if corrosion or excessive wear occurs. The stroke length of the polished rod can be measured at the top of the well. When the horse head is at its lowest point, known as bottom dead center or BDC, the polished rod and rod string are at the bottom of the downstroke. In a double pack stuffing box, 2 separate packing elements are placed in one box, allowing each element to be tightened separately. To replace a worn top set of packing elements, the tubing can be temporarily sealed by tightening the bottom set first. Then the top set can be replaced. The polished rod is normally lubricated by the fluids lifted from the well. However, if the well is pumped only part-time, or if there is a large quantity of separated gas in the well fluids, the packing may not receive proper lubrication. Now, insufficient lubrication causes overheating, which results in dry packing and fluid leakage. A lubricator may be installed when the stuffing box does not receive proper lubrication. The lubricator is installed above the stuffing box to supply additional oil for the packing. Oil is added to the lubricator on a regular basis or as needed. The stuffing box allows...
Okay, so this is the one of the method we use sucker rod pump to take out the oil from the bottom to the top. Some when the pressures are not enough. So well plumbing system. So just search this keyword and you will see a lot of oil well plumbing system. This one. You'll see wellhead and a lot of images here in this case. Okay. So this is the one method. The other one is the gas lift one, which is also very, very popular to lift the oils. What it does, it reduces the density of the fluid. If you have heavy oil, you cannot lift to the surface, do the gas lift. And again, it is very common here in states to do this kind of a job. And again, if you are working as a production engineer, artificial lift engineer, you will be working in the field with these companies on them. These are the production engineers looking into artificial lift. Can somebody translate from Arabic to English for me? So that was the two methods we just discussed. One of the rod pump and other one was the gas lift one. This is the gas lift one where we have the different kind of gas lift walls and we allow the gas to come from the annular space and goes towards the surface. So, okay, then as a production engineer, you definitely look at into the problems that we might face during production. It's not really a smooth journey. We might have a problem of asphalting. So you see, asphalting is a solid particle. You see, can block the pipelines and tubings and so on. You might have some other wax problems and going on, which can cause the formation damage as well as the pipelines damage and so on. We might have some sand production. Sand is a small sand like the one we have at beaches. Same kind of sand can come from the reservoir to the surface. And if it comes with very high pressure, it can destroy everything in between. Your Christmas tree, your tubings, can really do a lot of damage. So it's a nightmare situation if the well is producing sand. And it means that we have to kill the production because it will really damage the equipments and assets that we have at the surface. So these are the problems. Sometimes there's a perforation blockage can happen. So these are the well intervention engineer's job to come to solve this kind of problems or work over when they have to intervention, they have to do the intervention and solve these kind of problems and so on. So we just talked about the fundamentals, like we didn't go detail each part that we have discussed here. If you just touch, let's say, the well performance part, it's a whole complete chapters out of it. You can learn the engineering behind it. If you look at the asphaltene problem, it's just a whole another chapter. You can find a lot of work on it. If you look at the artificial lift system, it's just another all story going on. If you look at the fracturing one, the one I showed you the videos, is just another complete dimension. So we can do a specialized training thing just on a specific topic, because as I said, when you work as a production engineer, you will be dealing with one of it, not all of it. So you then, because all of them needs a lot of experience, a lot of knowledge behind all what is going on. So that was the fundamental production system concepts. Now we will connect those concepts with our problem, which is the asphaltene precipitation, and we'll see that how effectively we can handle this kind of problems and what kind of graduation projects you later on you can take on the subject, which will be able, you will be able to solve it. So do you have any question for now, or we can take some break, or we can continue? Please suggest me. So on, because I will need like 30 minutes more to on the asphaltene precipitation topic. So right now, the idea was just to give you the background for the production system, to tell you how production system works, what are the production engineers, what they are doing as a production engineer. So just an overview, but each one we can go in details. All right, guys, then we can take a break, 15 minutes. Right now, probably you might have a time of 6:30 you have right now. So let's meet at 6:45. 6:45 p.m. here. Is it fine?
Guys, we will continue after 15 minutes. Okay.
Okay. And meanwhile, if you have any questions, you are most welcome. Also, I will share my email with you. If you need anything, we can discuss about production engineering. You're more than welcome and to see what's going on. Okay, so you can start again. Can we start?
Yes, we can start now.
Okay, so let's start and talk about the asphaltene precipitation and what it is. As I mentioned earlier, that asphaltene is a solid particle. It's a part of a crude oil. It's part of many crude oils. And once it precipitates, you can see how problematic it can be. It can plug all your pipelines. So if asphaltene takes a place inside like this, then how you can produce oil? Oil will be filled with the asphaltene. So that's a very serious problem. You can see here how much is the diameter is reduced. So asphaltene can do disasters. It can create a lot of problems, and this is how it looks. The asphaltene. This you can see here. Now, what happens? Initially, asphaltene is not really a problematic. It's just a part of a crude oil, but well dispersed properly, small. You don't really catch it. What happens if the pressure drops? And how the pressure drops? If you are producing over time, after 2 years, 3 years, 4 years, the pressure starts to drop. And once the pressure is dropping, the asphaltene will make a separate phase like this small. And once the further pressure is dropping, you will see the asphaltene will make big particles. And once it becomes these big particles, they can settle down in the reservoir and block the pore space, reduce its porosity, permeability. And so it changes the viscosity. Viscosity is increased, porosity is reduced, permeability is reduced, relative permeability is changed. So asphaltene really, after it precipitates in the pipeline, it can go in this kind of form. In the reservoir, it can do this kind of plugging kind of a thing, say, and so on. So it's really a big problem. Now, this is the same pressure drop picture, which we talked about in the first session. And we talked about the pressure losses happening from reservoir to the surface. We definitely did not consider the effect of asphaltene. Imagine if there's an asphaltene like this one inside the reservoir, it means you are dead. You cannot produce. Yes, it is one of the flow assurance cases. That's correct. So here you can see. Now, flow assurance means you have to assure that the flow continues. So if there's asphaltene inside the tubing string, means that you cannot flow properly. The oil cannot flow properly. So asphaltene can block the pore space, can reduce the permeability, and especially in the near wellbore. This problem is mostly near the wellbore, near the perforations, because there's a very high pressure drop there, which can cause the asphaltene to precipitate. And then this asphaltene, when it moves up inside the tubing, the solid particle, as you see here, it can create a channel like this, and how the oil will flow. And the same goes on inside the separator, the storage tank. The asphaltene will keep doing disasters wherever it goes and malfunctioning, and that's the problem. So there will be whatever pressure losses we talked about here, there will be more further pressure losses which will be caused by these solid particles that are accumulated. That's why it is very important that we manage this kind of problems in our fields and manage this asphaltene in this one. So how this happens? What causes this kind of problem? It could be because if the composition is changed. How the composition is changing, maybe you are doing the water injection in EOR cases, or you are injecting the gas. So these kind of changes in composition, immediately asphaltene will precipitate and make a form like this one inside the reservoir, and it can cause the problem like this one. So one of the reasons from this to this can happen is just change in composition, because you are injecting additional gas or water or something which can change the composition and so on. The other thing is the pressure effect, because once you reduce the pressure, the asphaltene can go from this phase to this phase. So, and definitely it is very natural that over time when you produce, the pressure reduces. So if the pressure reduces, so this can happen. The asphaltene can come out and create problem. Other one is the change in temperature. As the temperature is reduced, okay, so or increased, the asphaltene is changing, sometimes above, sometimes down. So temperature really has an effect on asphaltene precipitation also. I use the word precipitation. Precipitation means asphaltene which was dispersed before uniformly. You cannot see it here. Makes a small droplets like what you see here. We call it a precipitation. And once it makes bigger stone-like shape like this one, so we call it a flocculate. And once these flocculate goes, can deposit inside the reservoir, in tubing, as you see, reservoir, tubing, flow line, separators, and it can do the disasters there that of the flow assurance. So that's why it's a real problem of industry. Whether you go to Middle Eastern country, whether you come to United States, whether you go to China, to major fields, whether you go to the Asian countries. So you will see this kind of problem happening many of the places. So, and it's a very hot research topic. And my work right now, what I'm doing research is on asphalting at the same time. Okay, now we talked about the effective strategy. We said that, okay, we are going to discuss how we can manage this kind of a problem. I hope right now the problem is clear to you that we have a solid particle, it can really do the disaster. So now we as engineers, we as a scientists, how we can handle this kind of problem. And this is happening because of the change in composition, pressure effect, temperature effect, and what can we do it? Well, the first step to know about this asphaltene, you must first know whether this can precipitate or not, whether your oil that the field you are working has the asphaltene or not. First thing you must know this thing. So when you look about the evaluation of stability, first you check the oil in your laboratories, whether it has asphaltene or not. This is the first thing. Once you know there's an asphaltene, okay, we know it has an asphaltene, like these particles, it has some. How much it has, and whether it can create problem or not. This is the second thing the second question you must ask. So, okay, we know there's asphaltene, okay, so whether it can precipitate or not. So again, we have to check in the lab, and then we have a colloidal instability test. There's one equation that I will show you right now. We check through that whether it has a tendency to destabilize or not. This is the first thing. Second thing that we do some lag experiment, and we do some simulation modeling to find out at what pressure and temperature this can happen, or at what composition this can happen. So this is the another thing that we find out, that at what pressure, at what temperature this is happening. So we have to predict at what pressure, because if you know your reservoir pressure is 2000 psi, and we know from our prediction asphaltene will precipitate at 2100 psi, it means that you have crossed this level, and it means that there is some damage in the reservoir, because asphaltene must be precipitated, because we predicted that at 2100 the asphaltene should be precipitated, and right now the pressure is 2000 psi. So it means that asphaltene must have precipitated in the reservoir, and we should do something in order to increase our production. Remember what we talked about. As a production engineer, we have to increase our production, try to maintain long life of the reservoir by reducing the problems that we have. And one of the problem is asphaltene. Or maybe we can look into some programs to clean up our pipeline and so on to asphaltene. Let's look at the composition. Look at the how can we find out that there is an asphaltene? So we have a test called saturates, aromatic, resin, and asphaltene test that we do. We find out the saturate content, aromatic content, resin content, asphaltene content, and then we have a equations, colloidal instability index, where we just add the numbers here, and if the value is 0.9 and more indicate oil with unstable asphaltene, value with 0.7 indicate stable asphaltene, and between 0.7 to 0. It's uncertain. So it's not really sure, but still we use it to find out this SARA thing here. This is one of the methods. So how we do this saturate, aromatic, resin, and asphaltene test, we have equipment here in the lab. We call it HPLC. Now this HPLC basically tells us that whether we can, how much it has saturates, how much it has aromatics, how much it has resins. And the fourth thing, asphaltene, we find out through the N-hexane method. We'll talk about it, how we do it at the same time. So this is the first step. When we are talking about the effective strategy, we must know whether the oil has asphaltene, how much it has, does it has tendency to destabilize or not. So we do it usually by looking at the composition of asphaltene, and we do the SARA analysis. And later on, we go for the pressure depletion experiment. I'll just talk about them after that. Now, this is the another test for the asphaltene. What we do, we take oil inside the container and we mix it with the heptane, just pure heptane. Heptane, as you know, is a carbon, is a hydrocarbon. It's a pure hydrocarbon. We just take the heptane, we just mix it with the oil, and once you mix it, then the asphaltene particle will come out, as you see here. So it tells us that it has asphaltene and it has tendency to destabilize. This is what we can find out through the. Some of the heavy oils, most of them they have it. Most of them, not all. Most of them they have it. Even light oils, they have the hydrocarbon. So it doesn't matter the oil is heavy or light. Still, it can precipitate. Still, it can be stable. So it doesn't matter. For me, I have worked on both of the oils, light oils as well as on the heavy oil, and both have the tendency. Even it doesn't matter how much asphaltene it has. Sometimes, for example, the light oil might have 7%, 7-8% in the oil, and the heavy oil probably have 5-8% into it, or maybe 8%. So it doesn't matter how much weight percent it is. When it wants to precipitate, it precipitates. That's all we know as an engineer by now. Okay, so there are multiple studies, the effect of regions, the effect of, how this precipitates. So there's long research going on. But for now, asphaltene, it does not matter heavy or light, it just precipitates in both cases. And it can happen in both kind of oil, light oil and heavy oil. And I have seen both of them in this case. So how we find out the asphaltene, we just add heptane and we mix it, and that's how we get the saturates. And this one, resin, aromatics, and saturates, we use it to find out through the HPLC. Asphaltenes, we find out through this method. After we do this method, we have this equation. This equation will tell us that whether it can destabilize or not. Okay, now this can destabilize. We got to know that the oil we have in Egypt, we tested this oil, we did its SAR analysis, and under HPLC, we'd find out through the heptane, okay, this can destabilize. What to do next? Now, the next step, you must try to know that at what pressure this is happening. So for that, we have a Pvt experiment. We have equipment called Pvt Experiment, and Pvt is equipment that is used really in big universities. You might find Pvt equipments, and it is what it does. It is a high pressure container. What it does, from the high pressure, we just reduce its pressure in small steps. For example, in the container, the pressure we can keep like 5,000 psi. And then in a small steps, we reduce every 5 minutes, 200 psi, let's say, or every 10 minutes. And we look at through the window or from the computer camera that how the oil is looking inside the chamber where we kept under high pressure. So this is the equipment that we have, Pvt equipment we call it. And using the Pvt equipment, we can find out that we depressurize the oil and we see at what pressure it is formed. So this kind of experiments we do, and then we have results like this one. So as you can see, this is the light transmittance. So what we do here, we have our sample chamber. This is a glass. We have our sample inside this one here, and this is high pressure, let's say 5,000 psi. So what we do, we have a laser light, the laser light you see, we have a source of laser light which is going from this direction, and it has to pass through this, and it passes through this one. Now this laser light which is going through this sample is recorded through this graph here, at what pressure. As you can see that there is no disturbance in the laser light, it's just straightforward in the Pvt. It means that asphaltene, if there is a solid particle, it will definitely disturb this line, this light transmittance, because solid particle, the light cannot cross. So if the light cannot cross, there should be some disturbance here. So we don't see any disturbance in this light. It means that oil is quite stable. It has no asphaltene precipitation in this case, and so on. So what we do here, in the next step, we added some more gases. We added, let's say, we change the composition. As I said, there are 3 factors that can cause asphaltene to precipitate: change in composition, change in pressure, or change in temperature. In this case, we change in pressure, nothing happened. But when we change the composition, you see there's a severe drop of, here in this section, there's a drop of light transmittance. Means light couldn't pass that area. Why it couldn't pass? Because definitely there's some solid formation which did not let the light transmit from one place to another place. So light was disturbed. So that is the reason we said, okay, at this pressure, the asphaltene start to precipitate. So we do this kind of test in the laboratory under the Pvt experiment. After we find out from the simple test, okay, we have an asphaltene, it can destabilize, it can create problem. Let's look at what pressure it does that. So we go for the Pvt experiment. We find out, okay, we have a problem of asphaltene precipitation at this one. Okay. Once we have those testing, we develop this kind of envelope. Now let's look at the envelope, what it has. This is a typical reservoir engineering Tariq Ahmed phase behavior diagram. We have a pressure, here we have the temperature. Let's look at what is the red line here. Red line is the bubble point pressure. What is the bubble point pressure? It is the first drop of bubble or gas which comes out of the solution or liquids. So this line differentiates between two zones. One is this zone here. One is this zone here. One is this zone here, and another is this zone here. So this line separates one or two zones. In this zone, we have only liquid. And below this zone, we have two phases, which is the liquid and gas. Gas and oil. So that's why the bubble point is important, because it tells us that whether the oil has two phases or the one phase. One phase above it means it's only liquid, below it's two phases. So what is happening here, when we do the Pvt experiment, we generate the upper asphaltene onward set curve, means at what pressure asphaltene comes out of a solution. And at what pressure asphaltene can become from this point to this point. At what pressure? So that pressure is recorded here by this line. This is its upper limit and this is the below. So if our oil pressure is in this zone, in this area, it means we have some asphaltene. If the oil is above it, we don't have any asphaltene problem. So in our research right now, we are developing a new mathematical equation, and we have developed, and it's under publication stage, that can tell us that at what pressure asphaltene can come out. This is what we are doing right now here in Missouri University. So here is the liquid and asphaltene things going on, and below the bubble point, we have asphaltene, we have the gas, and we have the liquid as well. So this kind of diagram is very important when we deal with asphaltene phase. So why it is important? Because, for example, you have the reservoir and asphaltene has destabilized and it can cause the precipitation. It has caused the precipitation here, means there's a blockage, means your oil cannot flow. So we already predicted at 2000 PSI this will happen. So we now know that there's a problem in the reservoir, there's a formation damage, asphaltene has caused, and we should do something about it. What can we do? We definitely can go for hydraulic fracturing. We just discussed in the previous section. We can do the hydraulic fracturing job in order to create the fracture, or we can do the acidizing job to do this one. One of my previous research was to inject some chemical inside this reservoir, so that the asphaltene should not precipitate, it should keep it dispersed. And we were quite successful in that, to find an inhibitor which can keep it dispersed in that phase and so on. And my other job is, why not we find a chemical or inhibitor or anything that should not let this happen, and that should keep it like this. So this is a research. Maybe if some of you can work on it in your graduation project, in your master's project, or in your PhD projects later on. This one. Now, this asphaltene, once precipitate, can create this kind of a problem, as you can see here. So what should we do with it? How can we remove it? So we have three ways to remove this kind of situation here. And we have chemical methods. We inject some chemical in the pipes. We have some mechanical methods, and we increase the temperature to melt it down. In chemicals, we usually have dispersants, and especially toluene and xylene, we use in order to redissolve the asphaltene deposits. So we can use in the pipelines, the toluene or xylene, it can just flush us all the, so we keep injecting in the pipeline so that asphaltene do not accumulate. It go back inside the oil, and oil goes to the storage tanks, and from there we separate them somehow through the modern nowadays the separator has the solid parts also. Like previously what we studied in our courses, we have separator, oil, gas, and water, but now we have fourth element in the separator, which is the solid particles. So we have now separators which can separate asphaltene as one. No, asphaltene fracking will just, open the fracture. It does not let asphaltene to stop the asphaltene to precipitate again. So what can we do here? For now, we are very much scared to put any chemical inside the reservoir because of more formation damage can happen. So what we do now, we just do the cleaning up. So it will not, it will not solve the root cause problem. Asphaltene will be there and we cannot do anything. We just can do the cleaning and keep the well flowing, and that's all. That's all we can do so far. But of course, this is a good topic you have find out, and you can work on it in your masters. Maybe you can solve it in the reservoir somehow. So you need a research on it. That's what I'm here to discuss. That there are research areas that you can work on. This is one of the area that you can work on that you just mentioned right now. So root cause problem, how we can solve it? Either you just keep the pressure above the asphaltene precipitation pressure. And how you can keep it? It's very hard to keep it. There's no way you can maintain the pressure above asphaltene precipitation pressure so that asphaltene do not precipitate. This can happen. Okay, and then we have the chemical methods, and we inject chemical asphaltene inhibitors, as you can see here near the wellbore, and it just dissolves it there. This is the chemical treatment method that we do. And at the surface, we just use the toluene and xylene to keep the pipeline clean. Just use these two, do not go. And I tell you, some of the people even don't know these names. And they just hired some companies from America, Dubai, or somewhere to do the pipeline cleanup. And they don't tell them that we use toluene or xylene to clean up the asphaltene. Increasing reservoir pressure means you are injecting something, gas or oil, water. It changes the composition, more asphaltene will precipitate if you increase the reservoir pressure by injecting some other gas or oil inside the reservoir. So it means you are changing the composition. If you are changing the composition, asphaltene will precipitate. That's the problem we are facing in this one. As I said, the coil tubing unit, we inject the asphaltene inhibitors. Purpose is to keep them dispersed. Other one in the pipeline the surface, if toluene and xylene is not solving the problem, then we have a pigging operation. Pigging operation is a rubber tool which we crosses through the pipeline and it just goes inside and take out all the asphaltene from inside it, as you can see here from the pigging operation. So there in pipeline, you might need the mechanical way also, as you see this pigging one. Usually every year you will see asphaltenic production facilities, they do the shutdown activities for a week. And every year they clean it up. So they have to clean it up. There's no way. So right now there's another research topic. Is there any way we can avoid asphaltene without shutting down? Yes, tubing has problems. So what we can do, we can clean it with these inhibitors. We can keep it dispersed. All we have to use is scratchers again. Yes, we have to use sometime mechanical equipment to keep it clean. Because asphaltene this is the well intervention engineer's job to clean up the production tubing and so on. In this case. So here is one of the jobs. So now another research topic here could be like how we can avoid the shutdown operations and keep the asphaltene. This is another problem. And then of course, we can heat up the pipeline to deposit and so on. So asphaltene is a big problem, as I shared with you, and it can be mitigated chemically, mechanically, but this is not a root cause problem solution, just temporary solution. It is costing a lot. It is costing shutdown of production. If you are producing 100 barrels per day, and if you close the production for 5 days, it means you lost 500 barrels, multiply by $50 per day as per today's price, you lost a lot of money. At the same time, you are investing your money in the treatments. So it costs a lot in the asphaltene. It definitely create problem for artificial lift systems, because they will choke down. I mean, there will be a lot of friction, and friction will cause wear and tear and heat up everything. So artificial is a big problem for artificial lift systems. So you have to design special for asphaltenic wells for these kind of systems. This is another good research topic you can do in your graduation project. Yes, this is what I say. First, take the oil sample. Okay, you must have oil sample in your hand. Go take it to the lab, induce it, precipitate it with the heptane, mix it with the heptane, and see it has the asphaltene or not. Or if it has it, how much it has it. Then you have to go to this pressurization test, as I discussed those effective strategy that first find out what oil you have, whether it can destabilize or not, whether later on you do your pressure testings, then you develop your prediction methods, and then you look at what you can do with it. And then of course, you have to prepare your cleanup procedures. And if you see there's asphaltene precipitation, definitely you need chemicals to clean it up, you need picking jobs and so on. So from the laws, no, there's no chance. No, there's no way. You can only take the oil sample and find out from there. Logs do not tell us about the liquids mostly. They tell us about the porosity, the other thing that there's water. They can tell us about the phases. There's water, there's oil, there's gas, but it doesn't tell us exactly what's going on. The only way we take the sample in our labs and oil sample and can tell us directly what are we dealing with this one. So that was the today's talk. We talked about the production system and we talked about the asphalting problem. And for me, we are working on right now here on prediction method. We are developing new mathematical equations that can tell us what pressure and temperature asphalting will come out. Asphalting can create problem. After how much time asphalting particles can be bigger in size, can be mathematically predicted or not? Not from the logs, but can we have a mathematical equation? Yes, we are developing an equation here in Missouri. And log basically doesn't tell about the fluid composition. Fluid composition can only be known by the fluid itself. When you do the GC analysis, or you like take the sample to the lab and see what's going on with the oil. But logs are a different story. Logs tells you about the what kind of rock you are dealing with, what kind of phase it has, whether it has water, oil, or gas, based on the density. Just tell you the density. So this kind of, it can tell you the leakages in the cement. There are fractures, there are not fractures. It can tell you there's a permeability damage, certain permeability damage by production logging tools. So it can tell you the temperature, it can tell you the logging tool can tell you the pressure, it can tell you the flow rate from each perforation, but not exactly the asphaltene particles. So, yes, so that was today's talk. It was just an introductory talk overall, and each topic needs more discussion here. Or I just open a door for you to open up any topic afterwards. Then that topics can be specialized and so on. The idea was just to give you what is going on. So there are a lot of topics we can work on. You can work on your graduation project for your master's and PhD. So if you need any help in your research topic, in your graduation project topics related to asphaltene, we can look into it. We can work on it together. There's no harm in that. So let me know if you have further questions, or we can stop the session. Yes. So I think that's all for today's one. So that's all for today's work. And, you can send me an email in my this is my email address. If you need anything, you are more than welcome to ask me, to discuss with me. And please give me your feedback also. I hope you like my presentation. I tried to give you some concepts. If you learn 20% of it, it's more than enough from one lecture, if you can get that much. But at least the videos were very informative, I'm sure about them. This is my email address. Thank you so much for liking it. And I just wanted to share my knowledge with you guys, share some ways how to do the presentations. I'm really glad that I talked with you. My objective was just to share. No image found. Okay, I can give you the private one. Use this one.
The attendance form in the chat box.